All right, well, I'll get started. Let me begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for your students and the nice weather. Just help us to understand your creation a little bit better and learn a little bit more about physics today, Lord. In your name I pray, Lord Jesus. Amen. All right, so lest I forget, I have an attendance sheet up here somewhere. Ooh, it's a fresh one. You can put a new date on there, get us started. Thank you. So any questions before I dive into some examples? All right. So we have, I hope you seen my exciting new notes for Chapter 5. A lot of that I've already done in class. Not everything, though, and it's also, in some sense, a merge of my previous lectures, 15, 16, 17, I think 18, maybe 19 even. One other thing I should mention, I'm changing my office hours so that my office hours end at 1:50 because I'm inevitably late to class if I let office hours go to 2. So I need to change that. So you can expect an announcement about that. So I'll add office hours somewhere else. But anyway, just thought I'd mention that while everybody's here. So let's see here. Example. Suppose you got a pulley, all right? And over that pulley there's a string. And you've got mass 1. And on the other side you've got mass 2, right? Then we can analyze this motion using energy. If we assume that the string is essentially massless and the pulley doesn't have any friction much to speak of, in this situation we can use energy analysis to explain what goes on here. So let's suppose that this down here is y equals to 0, all right? If I let this be, say this distance right here, let's say that's y1, and this distance right here is y2, then what would the formula for the potential energy of this system be? I have what? I have m1 g y1. That's my potential energy for the first one, right? What's the potential energy for the second one? Right, so plus m2 gy2. So that's the total potential energy, right? And what's the total energy here? So kinetic energy plus potential energy. In this context, I've got 1/2 m1 v1 squared plus 1/2 m2 v2 squared, right?
Are we assuming it's moving?
Could be. m1 gy1 plus m2 gy2. So that would be the energy, whether or not it's moving. Yeah? Now, of course, there are limitations to this being reasonable, right? Like, if there's a given length of string, if y1 gets to be too big, that means that, well, m1 has gone up over the pulley, right? So these equations cease to be meaningful at some point, right? But in context, they could be meaningful. Okay, so I guess in order to make a physics example here that we can all kind of understand together, we could do something like what? Like we'll assume that m1 is less than m2, and that, let's see here, initially the system is at rest, right? If we do that, then we can ask interesting questions like, what's the velocity later on then, right? So so let's see here. Also, we'll, set y1 equals to 0 to begin. So what I'm saying is, like, we've got basically M1's on the floor to start with, right? And M2's hanging up here somewhere. M2 has a larger mass than M1, so it's going to do what? It's going to fall. It's going to drag M1 up, right? And before, we would have done what? We would have calculated the acceleration, right? This is a constant acceleration problem. We could have solved it like that. Now we're going to use energy methods to find the, here's the question. Find the velocity when M1 is at, height h. So there's my question. So what I've written in black is true independent of my question, right? That's just conservation of energy for this system, assuming, of course, that the friction in the pulley is not, anything much to look at. And also I'm assuming that the pulley is massless. We'll later learn that if the pulley has mass, it also offers a sort of rotational inertia. It resists spinning as well. But we're not there yet. So for the moment, we deal with these very silly massless pulleys. Okay, so what's the deal here? What's my initial energy? Initial energy is what? M2G Y2, whatever the initial height is of M2. We'll say M2 is at Y2 to begin. All right. So that's our initial energy. Is there anything else? Is there any kinetic energy? No. All right. This is equal to then what? M1 G times the height I'm interested in, right? Plus M2 what? What is the Y2, so to speak? If you guys don't let me, maybe we, instead of using Y2 for the initial height, let's use something else, like, I don't know, pick a letter, any letter. L. I'm gonna pretend I heard an L. So if that's L, I put an L here. All right. So my question then, now that I can ask this question, what should Y2 be? What's the deal?
Ask the question.
What is Y2 here?
L minus Y1.
L minus H, right. And what's the idea there? How did you guys know that? Like, you only got so many letters. It's either got to be a sum or a difference of the letters, right? Process of elimination. Let's think about this differently. What would be Y2 minus Y1? Let me introduce yet some more letters. If you don't see it already, maybe this will help you. Let's call the length of string that's above M1 and below the pulley L1. And let's call the length of the string which is above M2 and below the pulley L2, right? We should have what equation? Yeah, I heard L2 plus Y2 is equal to L1 plus Y1, right? You might have said something different, but that's same idea. So what this then means is that well, L2 minus L1 is equal to Y. Well, let me not say any more. I think I've said enough. So really, L1 plus L2 is what, by the way? words. This is the fixed length of string, right? It's the length of string that's at play here. We're assuming the string doesn't stretch, so you're kind of stuck with that, you know? So I think that you guys are right. L minus H should be Y2 there. Let's see here. Because Y1 plus Y2 should be equal to what? Well, that's not the right way to look at it. L1, I guess I needed one more equation here before I stop my yammering about this. If I take this and if I look at, let's say, Y2 minus Y1, what's that equal to? L1 minus L2. I don't know if that helps or not. There's something else I'm trying to say here. I can't find the words.
L1 plus L2 equals big L?
Yeah, L1 plus L2 doesn't, but big.
The total height is equal to Y2 plus L2, where the total height is equal to Y1 plus L1.
I mean, I've said that here. Yeah. Agreed. But L is not the length of the string either. Big L is not. Big L is just the initial. As I've said it here, big L is what? It's the initial height of M2, right? Which is not the. That's not the string. Like, that's not the length of the string.
We said the mass length also,
It's the height off the ground for M2. What's that?
since we set Y1 equal to 0, wouldn't work out to just be L then?
Since we put Y1 equal to 0, wouldn't what work out to be L?
The length of the string.
The length of the string would be L.
Not necessarily. It could be,
Huh.
right?
Hold on a second here. So L2 plus, so this is the starting time, okay, at start. We have L2 plus, you said Y2 was L, right? Equals to L1 plus 0. So that means that the length, well not the length, the height of the string, the height of M2, which is L, is equal to L1 minus L2. But I don't think that's the length of the string though, right? The length of the string is certainly L1 plus L2, right? So no, I can't quite agree with that. Anyway, so my point is, this is the formula for the potential energy. How about the kinetic energy though? We still have what? 1/2 m1 v1 squared, right? Plus 1/2 m2 v2 squared. Does the kinetic energy care about whether it's coming up or down? Thankfully, no, right? This is just a scalar that depends on the square of the velocity. So now, here's something. Because, notice that, notice something here. If we assume that, well, anyway, I'm sorry. I'm missing an equation in here somewhere. But one other thing we should notice is that the speed of these two masses are linked, right? If the string is not stretching, if the one on the right is going up at 5 meters per second, the one on the left is going down at 5 meters per second, right? That's why it made sense for me to ask you to find v here, which you might have wondered, wait a minute, what do you mean v? I mean find the speed of the system, right? How much it's going up on this side, how much it's going down on that side. Either way, I can make both of these v, right? So altogether then, I have m2 gl minus m1 gh minus m2 gl minus h is equal to 1/2 m1 plus m2 times v squared. And if we're lucky, some things might rearrange here. Oh, look at that. See that? Something cancels here, doesn't it? See this? That cancels. And we're just left with if I haven't done something wrong. Huh. Okay, yeah, so M2GH minus M1GH divided by, all times 2, divided by M1 plus M2 equals to V squared, which tells me that V apparently is the square root of 2GH times M2 minus M1 divided by M1 plus M2. So it actually doesn't matter. It doesn't matter how high, and this makes sense if you think about it, right? It shouldn't matter how high M2 is off the ground when this starts, right? Well, it's one way to look at it. Like we should be able to completely describe the speed in terms of how high the M1 has lifted off the ground, which is what we've called h here, right? I'm sure there's another way you could write the answer in terms of, instead of in terms of h, in terms of like the final height of M2, right? These things are related, obviously. So that was, I just factored out a g and an h there. And let's stop and check this. Does this formula make sense? What would be something we could check really easily to check ourselves on the formula? The beginning? Oh, good. Okay, so when h equals to what? What's the beginning? Yeah, h equal to 0, the speed is what? 0. That checks, right? It's initially at rest. It can't jump to a non-zero velocity immediately. All right. How about this case? What if the masses are equal? What if instead of them being, instead of M2 being heavier than M1, what if they're equal? What happens? Yeah, they just balance. It just sits there, right? And then what else? Anything else we could see? You could do dimensional analysis. That's sometimes helpful. So notice that the masses, they be canceling. So you get like kilograms over kilograms. G is in meters per second squared. H is a meter. So you've got like meters squared over second squared inside a square root, which works out to a meters per second, right? So dimensional analysis says that the formula is reasonable. Anyway, what I'm showing you right now here, of course, is the Atwood machine, right? Did you guys do this lab yet? It's this week. All right. Well, some of you maybe have done it. Wait a minute. No. Is there any labs today? Nobody's done it yet. Well, this is good. So if they were actually equal, if you just gave it an ever so slight nudge, it should do what? It should just kind of slowly go, just whatever initial. If the masses are actually equal, you can kind of just go. And of course, in the actual lab, there is some friction in the pulley, so you could actually kind of account for that in terms of the motion and things if you're careful. All right. Anyway, enough about that. So my next example, I want to talk about springs for a little bit with you guys. And so in the interest of being mathematically complete here, I need to share with you guys a simple result from differential equations that once we know this result, we can just use it and we can solve this problem. All right? And it's not, it's not going to help you a lot with differential equations, right? Like, I think if you take a step back and you look at everything we've done with vectors in here, if you take Calculus 3 after you take this course, it's just going to help you because a big part of Calculus 3 is vectors, right? But this is not true here. Like this is a tiny, infinitesimal little sliver of differential equations. But here it is. So this is just a math result. If we have d squared y dt squared plus omega squared y equals to 0, then y equals to a times the sine of omega t plus v is a general solution. And by what I mean by that is if I give you the initial position and the initial velocity for y, that single formula has everything possible that can happen for this differential equation. So like, let me just give you an example.
Circle with the line here, what is that called?
Phi, just phi. 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 Yeah, this is phi. Like phi 5 pho phom. So you could also call it the phase angle. So, so like for example, and this example would be considerably easier than my first example. Suppose we were trying to solve, me use the prime notation, y prime prime plus 9y equals to 0, with y of 0 equals to 0 and y prime of 0 equals to, I don't know, 2. Great. Okay, so here's how that goes. We look at this and we go, apparently omega is equal to what? 3. Because I have, it's a square of omega that I'm seeing in the differential equation, all right? I see a 3 there because 3 squared is 9. So then, y is equal to a times the sine of 3t plus my phase angle phi. All right? Now, the a and the phi, a is the amplitude. Again, phi is the phase angle. How can I find the a and the phase, the amplitude and the phase? Well, simply use my initial conditions, right? That tells me what? It tells me here y of 0 is what? A times the sine of what? Phi, right? Okay, great. And let's see here. Let's differentiate this. dy dt is 3a cosine of 3t plus the phase by the chain rule, right? So this one gives me y prime of 0 is what? 3a looks like cosine of the phase angle phi, right? Now these are given, for this problem, they're given to be 0 and 2. So now we've got to solve these equations. It's a little bit of trigonometry, but we can do it. What should phi be? If you want sine to be 0, what do you, I mean, the amplitude here cannot be 0 if you think about it. If we make a equals to 0, this all breaks down. So it must be that a is non-zero, and if a is non-zero, that forces the sine of the phase to be 0, right? So what's the phase equal to here? There are many choices, but how about this? We use 0. Because sine of 0 is 0, so that will solve that first equation. Once you know that the phase angle is 0, this equation becomes what? 3a times the cosine of 0, also known as 1, is equal to 2. Apparently my amplitude is 2/3. Let's put this all together. We have y of t is equal to 2/3 times the sine of 3t. And there you go. That's the solution here. Why am I talking about this? I'm talking about this because this is exactly the mathematics we need to describe the motion of a spring without friction. So what's a spring without friction look like? Right, guys? So what's the spring force? Do you guys remember? Yeah, F equals to minus kx is what I was looking for. And so if we're talking about one-dimensional motion, right, like this, then we have mass times d squared x dt squared equals to minus kx, right? So if you look at that, we can rewrite this, right? This is what? This is d squared x dt squared plus k divided by m times x equals to 0. So Newton's second law for the spring mass problem is that. So let's rewrite it so that it fits our standard template solution up here, right? So we've got d squared x dt squared plus omega squared x equals to 0, where omega is what? Where omega is the square root of k over m. All right? That's the spring mass problem. To solve it, we have to solve this second order differential equation, which isn't a big deal because you can just guess that the solution's a sign, right? And once we do that, well, let's write down the equation. What's the solution here? X of t is what? Some amplitude times the cosine of, my bad, not cosine, but sine of omega t plus some phase angle, right? Where what? Where omega is the square root of k over m. Now, omega is called the angular, the frequency, the angular frequency in particular of the system. We typically measure it in terms of radians per second because we're using sine and cosine defined by radian measure here. All right? So that's the equation of motion for the spring. Now, what the particulars are depends on where the spring starts, right? Is it compressed? Is it stretched? You know, what's the initial velocity of the spring? So, for instance, we can kind of piggyback on top of my example 2 here, and say, like, how could we end up with a situation x prime prime? So example 3 here. How about this? If I put the mass is equal to 1 and the spring constant is equal to 9, then we face what? D squared x plus 9x equals to 0, right? That would be Newton's second law that I had to solve here. And if I suppose, suppose that the spring is initially in equilibrium, but it's moving. All right, so it's moving to the right at 2 meters per second. So x prime of 0 is 2. If all that happens, we're right back to the mathematics we already did today. And what's the solution? So I need to get my other board back. I can't teach physics on 2 boards. It's just messed up. This room is dumb. I think we've gotten through our adolescent phase with the technology in here, maybe. So it may be permissible for me to put my board back up if I'm lucky. 2/3 sine of 3t, right? That would be the solution to that physics problem. All right? We have an amplitude of 2/3, and the angular frequency here is 3. So the spring mass problem, we can say a lot more about this, right? So let's talk about it. So I just got done telling you the equation is something like amplitude times the sine of omega t plus phi, where omega is the square root of k over m, right? if that's the position of the spring at time t, what's the velocity? And can you guys tell me what the period is also? Like, what's the period of the motion here? So this omega is angular frequency. So what that means is it's equal to 2 pi over the period. So the period of the spring motion is equal to 1 over 2 pi, let's see here, square root of m over k, I believe, if I did the math correctly. Does that make sense? So I'm putting t over there. Oh, good grief. Let's try that again. Solve for t. We get what? 2 pi divided by the square root of k over m, right? Which we can simplify. The period is 2 pi. Ah, man. 2 pi, the square root of m over k. All right, great. So that's the period for a spring. If you study this formula right here, right? If you want to look at it, you can easily verify by trigonometry that x of t plus big T is equal to x of t for all time. So the motion is periodic. It cycles back to where it started. All right? Let's move on here. What's the velocity? Well, v is dx dt, right? Which by the chain rule is a omega cosine of omega t plus the phase, right? So what's the energy of the spring? Can we talk about that? What's the energy? I heard a 1/2 kx squared. So E, it's equal to potential energy plus kinetic energy, right? What's the potential energy of a spring? We're assuming no friction here, right? If we add friction to the mix, then it really is a differential equations problem, all right? So I would be out of place to talk about it here, more or less. But so the potential energy, we worked this out the other day, is in fact 1/2 kx squared, right? That's the potential energy. That's the spring potential. The kinetic energy here, 1/2 mv squared, right? But you notice that we actually have formulas for this. What's the energy at time t? See, we have the formula for x. We have the formula for v. We can plug those in here and see what happens. What happens? So we've got ourselves a times the sine. Hey guys, to save ourselves a bunch of writing, let's call the argument for sine and cosine theta. Sound like a plan? Let's call this whole mess here theta. Save us a bunch of writing. So this is a sine theta squared, right? Plus 1/2 m. V was what? A omega cosine theta quantity squared. How are the m and the omega and the k related? Did you notice? Look here. This tells us what? This tells us omega squared is k over m. Or if you like, m omega squared is equal to k. That's nice to know. See, because I can swap out m omega squared here, and I can rewrite this as 1/2 k a squared times sine squared theta plus cosine squared theta, right? So I could simplify this, and I can get 1/2 k a squared is a formula for the energy of the spring, right? What if I simplified the other way, though? What if I simplified the other way? What if instead of getting rid of m, I got rid of k? What would this been if I had kept the k? Excuse me, kept the m instead. Omega squared is what? K over m, right? So I could have also written this, k is 1/2. My point is I could also write, let me just get to the point here. This is also 1/2 m a squared omega squared, right? Because k is m omega squared. And this, let me rewrite this a little bit differently. This is 1/2 m times a omega squared. What's the significance of a omega? What's the significance of a? Let's write it out. A equals to what? A omega equals to what? In terms of the motion. Let's think about it. I'm assuming A is positive here, guys, okay? Just for the sake of, discussion. We can always choose the amplitude to be positive in these. Let's make that assumption. So what is A? If I picture the spring, right? And here's x equals to 0. And here I've got v equals to 0. A is not the frequency, no. If my velocity is 0, what does that mean? The spring is what? It's stretched out as much as possible here, right? Past the equilibrium point. So that distance, whatever that is, that's the amplitude, right? That's the maximum stretching. And conversely, it, compresses in the same way, right? So this distance right here, x equals to minus a, when it's maximally compressed. So what is A? A is equal to, you could call it this way, it's the max x. What's A omega? By the way, we also assume omega is positive. We can do that without loss of generality. We're always going to assume that the amplitude and the frequency are positive, or at least non-negative. It may be in somewhere in engineering you talk about negative frequency, but I'm leaving that to the engineers. I don't want to think about it. Too hard for me. So A omega, look at this. How about this formula for the speed, for the velocity rather? When is this biggest? When cosine's 1, right? What is A omega? A omega is the max velocity. And this formula right here expresses a lot. There's a lot this says. This formula tells a story. This formula tells that the energy in the spring, you could look at it as the energy that's completely stored in the spring when it's maximally stretched out or maximally compressed, right? Because plus or minus a both square to this for x. What's this here? This says that all of the energy is kinetic. That's the energy that the spring has as it's passing through the equilibrium point. When it has no potential energy in the spring, all of the energy is kinetic, right? That maximum speed for the spring happens as it's passing through the equilibrium point. I haven't pictured that, right? But there are two things to picture, right? You could have like this, or you could have like this. What are the two different cases? Either it's coming or going, right? You could have the velocities like this, A omega, right? Or you could have the velocities like this, minus A omega. As the mass passes through the equilibrium point, anyway, when the mass passes through the point which makes the spring at equilibrium, whatever that point is in the motion, that's where the speed is maximized, where the velocity is either largest in the positive sense or largest in the negative sense, either right moving or left moving, as I've set it up here. All right? Any questions? So all of these formulas, you need to work the last problem in the homework, right? Because it's about a spring mass problem, and I ask questions about like the amplitude, the frequency, the period, all this stuff. All right? So I don't think you can fully understand these formulas, right, without properly doing the differential equation. And I'm not sure I've properly done it. I could derive that for you, but that wouldn't really add anything to the class. I think it's better for us to just state this as a theorem that we know from math. So we're going to do that here. All right? Any questions? So we can also draw the energy the diagram for the spring, right? What's the energy diagram for the spring look like? Uh-oh. Did I ever move the camera? I feel like I did. I don't know. Oh well. Hopefully I moved it. If I didn't, well, sorry. So the energy diagram for the spring is really pretty simple, because what's the potential energy look like? So potential energy for the spring looks like this, right? So if I draw right beneath it here, the XV plane. So here we're looking at U equals to 1/2 kx squared, right? We can draw in some energy levels, like so, and like that. Then another one up here maybe. Like that. And one more for good measure. All right. So what's the corresponding trajectories down here in the XV plane? We have just like a little ellipse or something, all right? All right, so the trajectories go rightward when they're above, and they go leftward when they're below, because velocity dx dt is positive, means it's going to the right. And if the velocity dx dt is negative, it means the motion is to the left, all right? And so these little loops in XV space, they tell the story I was just telling you in a disjointed fashion over here, which is that as the spring goes around its motion, these different points here, if you were to pick, these points, like this point, and this point, and this point, and this point, let me call these points 1, 2, 3, and 4 for the sake of discussion. 1 and 3 have V equals to 0, so the potential energy is maxed, right? On the other hand, points 2 and 4 in my picture have x equals to 0, so the potential energy is equal to 0, and in fact the kinetic energy is max. And so here we have the spring is stretching out like that, and it stretches out all the way over to here, maximally stretched, and then the spring pulls itself back in, and then we have velocity goes leftward here. It compresses to its maximum compression at 3, and then it comes back and just keeps going round and round and round in the XV plane, corresponding to the actual spring going back and forth. This is the meaning of these diagrams. Now, the spring is a very important example, which is why I've gotten into some details here more than I do sometimes for other things. In part because a lot of times the physical system is such that it can be understood as like a spring in some approximation. So pretty much, if you have, so this is just a comment here, example, let me just draw a picture. So if I had, hypothetically some other potential energy diagram, and it looked like this, right? If it looked like this, if this was my potential energy diagram, if you studied the motion of such a system, all right? You can, for all intents and purposes, if your initial position is like close to any of these potential wells, these are potential wells. So like if I was like in here, or if I had an energy level which was like here, or an energy level like was here, any of these points, x1, x2, or x3, these are all examples of what are called stable equilibriums for the potential. Effectively, the system behaves like a spring close to these points. So what's going to happen is you're going to have sort of an oscillatory motion if your initial position is close to these points for a problem that had this potential energy. On the other hand, if your initial position put you at the top of one of these hills, then you'd have what's called an unstable equilibrium, because remember the story, F is equal to minus du dx. So all of this, we're talking about a one-dimensional problem, guys. So the spring is a one-dimensional problem, at least as I've talked about it today. I mean, you could think about a spring in 3 dimensions and add 3-dimensional aspects to the analysis, but that's not what we're doing at the moment. Since F is equal to minus du dx, when the potential is increasing, that makes the force go to the left, right? U increasing implies that the force is less than 0. U decreasing implies that the force is positive. And here, positive is rightward, and negative is leftward, left-directed, right? So think about what that means. If I have a physical system with this potential energy diagram, if I start at the top of a hill, if I go a little bit to the left of that top, the force is going to be leftward. It's going to push me further off the equilibrium, right? On the other hand, if I'm a little bit to the right of that top point, the force is going to push me that way. So either way you slice it, here you're pushed that way, or there you're pushed that way. So if I start near the top of one of these potential hills, physics says you're going to get pushed away from that point. In contrast, if you're close to one of these potential wells, the force pushes you back towards the bottom of the potential well, right? Because the force is increasing, the du dx U is increasing here, which means the force goes left. U is decreasing here, the force goes right. And what that means is that for all intents and purposes, the system behaves like it's a little spring if you're close to a potential well. So I'm going to show you how that works actually for the simple pendulum next class if all goes as planned. Sorry I started late. I will try to start on time next time. Again, I'm changing office hours a little bit, so that actually is more likely to happen. So thanks, guys.